Component level design is one of the important steps in the software engineering process. What is component level design? Component level design defines the data structures, algorithms, interface characteristics, and communication mechanisms allocated to each component. This diagram shows the steps of software engineering process. Here is the requirements gathering and analysis part, and then architectural design. Then comes the component level design. In the architectural design, a complete set of software components is defined. That is a bird's eye view. But in the case of component level design, each component and the underlying data structures, what we are going to use in the program, data structures, that is data structure which we are going to use in the coding, and algorithms, interfaces has also to be defined. It should be with well established guidelines to help to avoid the introduction of errors. A component level can be represented using graphical, tabular, or text-based representations. This component level design information can be translated directly into source code. That is, our intent is to translate the design model into operational software. After the component level design, coding begins. Then comes the testing part. And what is a component? As per OMG UML specification, a component is a modular, deployable, and replaceable part of a system that encapsulates implementation and exposes a set of interfaces. A component communicates and collaborates with all other components and collaborates with entities outside the boundary of the system, which are outside the boundary of the system. A component level can be represented using some intermediate representation such as graphical representation, tabular representation, or text-based representation that can be translated directly into source code. And different views of a component are, three views are the object-oriented view, conventional view, and process-related view. In the case of object-oriented view, that is what we are doing in the C program and C++ programs. That is, everything data types and functions, related functions are encapsulated into classes. Like that, component is viewed as a set of one or more collaborating classes. And each problem domain class and infrastructure class is to be elaborated to identify all of its attributes, operations, and interfaces. Also specify the data structures what we are going to use in the program associated with each attribute, and design the algorithmic detail required to implement the processing logic. Algorithm is the step-by-step procedure for calculating something. It is a finite sequence of well-defined computer implementation instructions. And in the conventional view, a component is viewed as a functional element or module. That is, main module can be divided into different sub-modules, and module is the main part of this conventional view, and which comprises the same thing that we are representing in another way: programming logic, processing logic, and internal data structures and interfaces. Interfaces means it's a shared boundary across which two or more separate components exchange information. Thus, we can both send and receive data through this interface. And a component serves one of the following roles: First one serves as control component, that is coordinates the invocation of all other components. It coordinates all other components and serves as problem domain component. Implements a complete or partial function required by the customer and serves as infrastructure component. It is responsible for processing functions, modules. And conventional software components are derived from DFD, data flow diagram. Each module represented at the lowest level of DFD is mapped to a module hierarchy. Modules are represented in a hierarchical way. Control components resides in the top, and functional independence is derived between the transforms. And third view is process related view. Here emphasis is made on building systems from existing components. It includes complete description of interfaces, various modules or functions, and communication and collaboration functions interface. And here is the component level design principles. First one is open closed principle. Here a module or component should be open for extension but closed for modification. That is, the designer should specify the component in such a way that it allows to be extended without any modification. And second is Liskov substitution principle. Here subclasses should be substitutable for their base classes. Grandparent classes are there, parent classes are there, and child classes are there. And a component that uses a base class should continue to function properly if a subclass of the base class is passed to the component instead. And next is dependency inversion principle. It depends on interfaces or abstractions and do not depend on concretions. The more a component depends on other concrete components, the more difficult it will be to extend. Next is interface aggregation principle. Many client-specific interfaces are better than one general-purpose interface. For a server class, specialized interfaces should be created to serve major categories of clients. Only those operations which are relevant to a particular category of client should be specified in the interface. And one important part is cohesion. Cohesion is single-mindedness of a component. That is, it implies a particular class or particular work. That is a component or class which encapsulates only attributes and operations that are closely related to one task. And our objective is to keep cohesion as high as possible. The kinds of cohesion can be ranked in order from highest to lowest. First one is functional. A module performs one and only one computation and then returns the result of that computation. Second is layered. A higher layer component accesses the services of a lower layer component. Next is communicational. Here all operations that access the same data are defined within one class. Similar one. Kinds of cohesions. Next one is sequential, procedural, temporal and utility. In the case of sequential, components are or operations that are grouped in manner that allows first task. Then after completing that first task, it will go to the second task, then next task, up to nth task. In the procedural, components or operations are grouped in a manner that allows one to be invoked immediately after the preceding one was invoked, even when no data passed between them. In the case of temporal, operations are grouped to perform a specific behavior or establish a certain state, such a program startup or when an error is detected. In the case of utility, components, classes or operations are grouped within the same category because of similar general functions but are otherwise unrelated to each other. And second is coupling. As the amount of communication and collaboration increases between the operations and classes, the complexity also increases. As complexity rises, it is difficult for implementing, testing, and maintaining software. Coupling is a qualitative measure which operations and classes are connected to one another. Our objective is to come down the or low, make as low as possible. And here a good software design implements clean decomposition of the problem. Actually, we are decomposing the entire problem into different modules or functions and arrange it neatly. Here, neat arrangement of these modules in a hierarchical way. And the primary characteristics of this neat module decomposition are high cohesion and low coupling. And here is the way to conduct component level design. First, identify all design classes, what you have done in the architectural design, that corresponds to the problem domain as defined in the analysis model or architectural model. What you have done in the architectural model, then identify all the design classes. Also, identify all design classes that correspond to infrastructure domain. These classes are usually not present in the analysis or architectural models, but these classes include graphical user components, operating system components, networking components, and data management components. And next step, elaborate these design classes that are not acquired as reusable components. Specify data structures when classes or components collaborate. Identify appropriate interfaces for every component. Data structures, interfaces, and elaborate attributes. What are the different attributes connected to that component? And define data types and data structures required to implement them. And describe processing flow within each operation in detail by means of pseudocode or UML, Unified Modeling Language activity diagrams. To specify data structures, interfaces, and define different data types, interfaces connected to each component. Also specify algorithms. And describe persistent data sources. That is what databases or files are connected to our problem. And identify the classes required to manage them. Develop and elaborate behavioral representations for a class or component. This can be done by elaborating UML state diagrams created for the analysis model and by examining all use cases that are relevant to the design class. Next, elaborate deployment diagrams to provide additional implementation detail. This illustrates the location of key packages or classes of components in the system by using class instances and designating specific hardware and operating system environments. Next step is factor every component level design representation and always consider alternatives. We can notice that experienced designers consider all or most of the alternative design solutions before settling on the final design model. They will analyze all the alternative design models and select the best one. Here is the structured constructs. First one is sequential, that is first task first. After completing the first task, it will go to a second task. And the if then else condition, here it will check the condition first. If it is true, then go to this condition, this task, then goes here. If the condition is false, it will go to else part. Then